Well, after the presentation of, let's say, the most important algorithmic and computational developments and the most important techniques in the class of nonlinear multivariate analysis techniques, we shall, in this last hour, do two things, I hope. The first one is to pay some attention to the analysis of statistical stability, or the statistical analysis of stability. And the second one is perhaps pay some attention to future development within the Gifi system, or closely related to the Gifi system, development of techniques for so-called causal modeling of path analysis. There are quite a few results on algebraic and analytical stability in the book by Gifi. I shall not talk about those particular topics here. They're usually quite complicated, and statistical stability analysis is both more important and probably more familiar. The techniques we use for analysis of statistical stability are three of them. The first one is the delta method, the second one is the bootstrap, and the third one is the jackknife. I think you must be familiar with at least two or three of these techniques, but just in case, I shall explain each of the techniques briefly before I start with examples of their application. These are all three essentially non-parametric techniques, by which I mean that they do not make specific distributional assumptions, and they apply in the way we have formulated them to all functions of counts, all functions of relative frequencies, of proportions. And of course, in the Gifi system, because we make all our variables discrete, because we always assume that they are measured with finite precision and consequently vary in discrete intervals, we only have a finite number of possible data values, and consequently all our data are counts of profiles, counts of in the cells of a multivariate contingency table, counts of the possible combinations of categories that actually occur. The model we use in this statistical analysis of the Gifi system is the model of n repeated independent replications of a discrete random variable, as I already said. So this is a non-parametric model in the sense that you do not assume a parametric family of distribution functions. You do assume a random sample. And of course, as I have said many times, especially on Monday, random sample situation is not very representative of many of the situations that we want to apply our techniques to. But if it happens to be applicable, as it is in some of these studies of the Central Bureau of Statistics, for instance, then you can use these stability analysis techniques without a bad conscience. If it's not applicable, then you should have a bad conscience. Most people don't have a bad conscience, of course, if they use these techniques, but they should have one. The last sentence here is important. We have R-independent repeated replications of a discrete random variable, which takes m possible values. That's a new use of the word of m. I used it before for the number of variables. Now I use it for the number of possible profiles. The profiles were the combinations of all possible category values, the number of cells in the multidimensional contingency table. This defines a vector of relative frequencies, which I write as Pn with a bar below it. There's a sort of a convention in Dutch statistics. We also have a convention in Dutch statistics that is to underline random variables. Of course, if you use this convention in Dutch statistics and you send your papers to English journals, then editors of English journals do not like that in particular, because they usually underline vectors. And Printers do not like it at all because they usually underline what must be printed in italic. So it's perhaps not a very happy convention from the printing point of view, but it's very convenient from the notational point of view because it gives you a complete alphabet which you can use for random variables and a complete alphabet which you can use for fixed constants. Okay. There are two things which we use for these vectors of relative frequencies. They're both asymptotic statistical results. The first asymptotic statistical result is the weak law of large numbers, which says that this vector of frequencies, relative frequencies, converges in probability to the vector of population frequencies, of the vector of population probabilities, the vector of which is written pi here. The second result that we use is the central limit theorem, which says in this context that if you normalize the vector of observed frequencies, relative frequencies, and you measure the deviation from the mean, from the probability limit, then this normalized version is asymptotically distributed as a multivariate normal distribution with a very particular variance-covariance structure, pi minus pi prime, where the first larger pi is a diagonal matrix containing the same pi's as the pi's over here, and the second pi's are the two vectors containing the population proportions. Now suppose that psi, I know that if the previous one was phi, then this must be psi. Suppose psi is any function of p, by which I mean that it's defined in the unit simplex of Rm, with values in Rt. If psi is continuous at pi, then we have this result. The psi transform of p bar n converges in probability to the psi transform of pi. So in this sense, convergence of probability is maintained, convergence in probability is maintained by continuous functions. Now this means that if you apply any technique, a technique is also some sort of function, any continuous technique to your sample, then if your sample is large enough, the result will converge to the technique applied to your population. So this is a form of consistency. Everything converges if the sample size increases to the result you would get when you applied the technique to your population. If something stronger, something more specific is true about psi, that it is differentiable, and I only need this condition locally only at the true value. If it's differentiable at the true value with a derivative, a matrix of partial derivatives g pi, then this result applies. Now that means that also multivariate normality is preserved by differentiable transformations. So convergence in probability is preserved by continuous transformations, but multivariate normality is preserved by differentiable transformations. Now this tells you that the result of your technique applied to your vector of profile frequencies converges to the correct value, the population value. You can also get that from here. And that the result will be asymptotically multivariate normally distributed with a variance-covariance matrix that is computable if you know the true population proportions, which you do not know, of course. Another result which has been known at least since Laplace, it says here, that refers to a quotation of Benzacri that I gave on Monday. Thus, in blue, any differentiable function of proportions is asymptotically normal, because the proportions themselves are asymptotically normal. Now something stronger, again something stronger must be assumed about psi. If psi is continuously differentiable in a neighborhood of pi, the first assumption we had it was differentiable at pi, so now it's stronger in two senses. It must be continuously differentiable and it must be in a neighborhood of pi. Then this matrix, the variance-covariance matrix of the technique, can be estimated consistently by using this very simple result. the G of P bar, which is the matrix of derivatives in the observed vector of proportions, which is computable. And this is the estimate of the variance-covariance matrix of the proportions themselves. This converges in probability to the theoretical variance-covariance matrix, for the very simple reason that the weak law of large numbers continues to apply to continuous transformations, and we have assumed here continuous differentiability, which means that these vectors of partial derivatives are continuous. Now this result defines the delta method. We know that any differentiable function of proportions is asymptotically normal. We also know that if the function is continuously differentiable, then we can find a consistent estimate of the variance-covariance matrix by simply substituting the sample proportions into the expression of the partial derivatives, and by substituting the sample variance-covariance matrix for the population sample covariance matrix. That defines the delta method. Now everything computed in Gifi, even if splines are used, is a function of the profile frequencies. The cells of the multivariate contingency table, the cell entries, cell counts, even if splines are used, because it's still true that your data are basically discrete and that you can collapse them over replications because you're assuming a random sample in this case. And consequently, the delta method can be used. The only things you need in order to apply the delta method is an expression for the derivatives of your technique and a program for computing these derivatives. Now, perhaps I should emphasize once more the fact that I'm thinking of a technique in terms of functions. A technique is a function which takes your data, and in this case the data are represented as a vector of frequencies, which takes your data and maps it into some sort of representation space. And I'm assuming here, I'm restricting myself to the class of continuously differentiable techniques, smooth techniques. And many of the techniques, but not all of the techniques analyzed in Gifi, are smooth techniques. The results are a continuously differentiable function of the input. This is what you need in order to apply the delta method. This means that there is a routine way, anybody can do it who can compute partial derivatives, and most people can compute partial derivatives. There's a routine way in which standard errors and confidence ellipsoids can be computed for our techniques. At least, again in red, at least if you're willing to assume that the data are some sort of a random sample. If the data are non-random sample, or not a sample at all, or not a random sample, or whatever, the confidence regions can still be interpreted as measures of stability. Why is that? Well, the confidence regions still give you information about the size of the partial derivatives. And of course, the size of the partial derivatives tells you something about how the representation changes if you make a small local change in your data. That's the definition of a partial derivative. Make a small change in your data, how does the representation change given by the technique? So the confidence regions, which are then of course not confidence regions, can still be interpreted as measures of stability if the random sampling assumption does not apply. It is also true that this delta method applies in many more situations than the simple random sampling situations. The only thing you need is the central limit theorem and some expression for the variance-covariance matrix. And of course, even if your data are generated by a dependent process, a Markov process for instance, you still have asymptotic normality and you have a computable expression for the variance-covariance matrix, so you can apply the delta method. Only the variance-covariance matrix will look differently from the pi minus pi pi that I just showed. Most of the things computed in Gifi, this is a simplification of the general theory. The general theory stops here. Most of the things computed in Gifi are actually functions of the Bird table C. And this is important. Why? If you're thinking in terms of profile frequencies, there are a lot of profile frequencies. If you have m variables with K1, K2, K3, and so on categories, then there are K2 times K1, K times K2, times K3, and so on profiles. And that can be a lot, of course. The Bird table is of order sum K over the variables, and has consequently sum K square, sum K between brackets squared entries, which is usually far less than the number of possible profiles. And of course, half of these elements of the Bird table is redundant. You can write the Bird table as a function of the profile frequencies in the following way, or in that way, not the following way, this way. Bird table is a linear function of profile frequencies, where these vectors here, the G's, are the columns, oh no, the rows, are the rows of the indicator matrix. This is another way of writing C is equal to G prime G, which is the way we wrote it on Tuesday, I think. Here the G prime G's are sort of collapsed over profiles and are weighted by the profile frequencies, but it's exactly the same expression, of course. Thus you can write psi of P, which is the result of your technique, in the form as a compound function, which is a function of P only via or through C, and you use the chain rule to differentiate it. Now this part is concerned, of course, but with computing the derivatives of your technique. And if your technique is a function of the Bird table, as most of our techniques are, then this result allows you to simplify computation of the partial derivatives. It's a very simple application of the chain rule and of the fact that the Bird table is linear in the profile frequencies. This often simplifies matters. Many other things, and by things I mean things computed by the technique, many other things are functions of the induced correlations, RJL. We've seen that many times. Last time when we were talking about this general function phi of the correlation matrix that you're trying to optimize. Many other things are functions of the induced correlations, and remember that the induced correlations were this quadratic or this bilinear function up here. The inner product of the bivariate frequencies of variables J and L with the two vectors of scores or quantifications. Now you can use this again in combination with the chain rule. I'm not going to read out these things because they're not suitable for reading out, but you can look at them. It's a straightforward application of the chain rule, of course, and also of the rule for the differentiation of products. If, and in red it says model. This is not always true, so now I'm talking about a special case. I was talking about a special case in which the results of the technique are a function of the correlations. I will now talk about a special case in which more is true. All regressions, all bivariate regressions are linear. We talked a great deal about this special case yesterday in connection with explaining the relationships between multiple correspondence analysis and nonlinear principal component analysis, and also in connection with fighting the curse of data production. And now we encounter exactly the same condition in connection with the statistical problems. Suppose that all bivariate regressions are linear. In this context, it means that this equation is true and this equation is true. Now, I'm not saying that it means that the bivariate regressions are linear, but the bivariate regressions are linear after quantification. In the population, there are scores which can be chosen in such a way that the bivariate regressions are linear. Those. Now, if this is true, the formula here above can be simplified by substituting for these two quantities up here from these down here. And again, this can be further simplified by using the fact that the restrictions are used that these scores should be normalized. Otherwise, the expression for the correlation coefficient, of course, is not a correlation coefficient, but a covariance. But we have worked in terms of correlation coefficient, so this one was imposed. Differentiate that. Differentiate the normalization expression. Just for J, it gives this. This here is a bit sloppy, but it's the P of mu. Yes. If you write it another way, you have this expression up here, and you can substitute that again in derivative, and you have a simplified expression which applies to all techniques that are a function of the induced correlation coefficients. The results are a function of the induced correlation coefficients. In the second place, there are scores which linearize all bivariate regressions. Then this formula applies. And now in red it says something extremely important. This is exactly the same derivatives as the one you find if the yj are known scores. It's the definition of the ordinary correlation coefficient for known scores. If you do that, if you substitute that, and you find exactly the same expression. There is no derivative of y with respect to p in this expression anymore. It has vanished by this trick up here. So this is a very important result because it shows you that the two-step procedure that we have talked about, maybe not in these terms, but I'll introduce the terms now. You use a quantification method to find scores. That's the first step. And then you use the quantified variables in some other multivariate analysis technique. Now, this result tells you that such a two-step procedure makes perfect sense if the scores that you have used are such that all bivariate regressions can be linearized. Because if that is true, the asymptotic properties of the estimates you get from your second step, from your multivariate analysis technique, which can be component analysis or multiple regression or whatever, are the same as they would have been if you had known the scores beforehand. So if you have fixed scores, for instance this 1, 2, 3, 4, 5, or optimal scores that has no influence on the behavior of the criteria that you're optimizing in the second step. In other words, another phrase, you cannot be capitalizing on chance if all regressions can be made linear. Of course, these are all asymptotic statements. And in finite samples, again, many things could happen which are not foreseen by the asymptotic theory. So this is important implications for primals, for instance. That's a technique which applies one-dimensional multiple correspondence analysis to a data set and uses the scores to improve the correlation matrix. Now this says that it really improves the correlation matrix and that this scoring procedure does not introduce extra error variance, does not introduce extra standard error if the regressions can be linearized. We are currently using this two-step procedure in combination with LISREL and similar programs. Of course, LISREL and similar programs can be used in situations in which the data are a random sample from a multivariate normal distribution. If the data are a random sample from a multivariate normal distribution, of course, all bivariate regressions are linear. Now, this tells you that the two-step procedure makes sense if all bivariate regressions can be made linear by scoring. The LISREL procedure, in a strict statistical sense, only makes sense if all bivariate regressions are linear. In fact, if much more than that is true, if the data are a random sample from a multivariate normal distribution. This tells you that the two-step procedure makes sense under much more general assumptions, that there are scores, which can be found by homogeneity analysis or any other of these techniques. If there are scores which make bivariate regressions linear, then you can use the two-step procedure and it will give you consistent estimates of your structural parameters. And that is, of course, a strong and very far-reaching generalization of the Lisrael model.
Jan,
Yep.
seems to me that with all the messing around we do with these procedures, that asymptotic probably really does mean asymptotic. And I wonder if it doesn't bother you to put together something that probably requires an enormous number of observations to justify, together with something else like Lisrael, which also is asymptotic and probably requires a very large number of observations to be valid, even starting out with something.
Well, you're sort of suggesting that if you put these two things together, then you need the square of the number of observations?
I'm suggesting that maybe you're one of the more optimistic people around.
No. This is, and well, I entirely agree with you on one point, and the point is, of course, that asymptotic results are of limited applicability. And you're probably entirely agreeing with me on one point, and that is that in many situations, asymptotic statistical results are the only realistic results around. There are no finite sample results for complicated situations like this. And if there are finite sample results for complicated situations like this, they're always based on the multivariate normal distribution, which never applies. This is, of course, a string of fairly complicated and strong statements, but I think it's commonly acknowledged to be true. There is, in typical multivariate situations in which nonlinear methods are used, the only statistical results around, and not only the statistical results around, but also the only statistical results which are thinkable and have practical relevance, are based on the multivariate normal distribution or asymptotic. And that's the choice you have to make. Now, it depends what's more unrealistic, the asymptotics or the multivariate normal distribution.
Well,
I don't know very much about that, except for the fact that there have been a number of studies with sample size as a criterion to look how relevant asymptotic results are, and there have been a number of studies with multinormality as a criterion to study how relevant the assumption of multivariate normality is. And the results are usually dependent on the model. If you have a very simple model, then you can get away with multivariate normality in many cases. But if you have a very complicated model, then you need a large sample, and then the asymptotic results apply, but not normal results. I think that's sort of a summary. The results will be model dependent.
well, it seems to me that the multivariate normality frequently isn't so much of a concern. And anyway, when we're talking, say, about a vector of proportions, it's easy to believe that a vector of proportions is going to go to multivariate.
Well, my results are...
rather quickly, but even if it didn't, I'm not sure that matters in terms of the statistics that we're looking at, which aren't, after all, generally not very sensitive to multivariate normality. But it seems to me
My results are based on multivariate normality of the vector of proportions.
But you can, you're talking about, say, a t-test.
I'm never talking about a t-test.
Or if you're talking about a regression analysis, you obviously can deviate a great deal from normality, and your computed t-statistic will be very nicely behaved. So
Well, t-statistic is a case in which... That is true. The t-statistic is a case in which is fairly robust against certain deviations from normality. That's well documented in the literature. So I would not suggest, if you have a continuous, fairly well-behaved variable as a dependent variable, and some categorical variables, whether you want to call them variables or not, as independent variables, then I think multiple linear regression with the whole statistical machinery attached to it is a perfectly respectable and probably quite optimal technique. I'm only saying that it's not the only situation that you ever encounter in practice. And if you want to do, let's say, inferential statistics, which is also according to my criteria, certainly not the only situation which you will be interested in practice, then sometimes you cannot use the multivariate normal gauge and you have to use asymptotic statistics. And that's not a very original or a very deep or observation. I mean, you can look at any statistics book or any multivariate analysis statistics book, and most of it will be concerned with asymptotic normality and not with exact normality. So many people will agree that the asymptotic situation is the one which is the most relevant for some applications at least. Okay. The implication that you need the square of the number of observations if you're combining two asymptotic techniques is of course not true. I mean, you need...
If you've got infinity, I won't worry about infinity squared.
No, okay, good. These results are all for infinite samples, of course, so there's nothing to worry about. Yes.
I was concerned that the net effect of the transformation as a function of the underlying probabilities might have a zero derivative in the neighborhood of the true probability, and then would be degenerate and have a stationary distribution.
Yes. That does not happen in the case of, you mean a situation which would occur if you're, for instance, if you're differentiating chi-square or some statistic like that. That would be a possibility. Some deviation type of statistic. Well, in this situation, I'm not thinking of yes?
Say Chimera type.
Yeah, something which measures a distance basically, and which is of a second order, which makes the derivative vanish in the neighborhood of the true solution. Well, in that case, you cannot use the delta method in this form. You have to use one step ahead, of course. You have to use the quadratic approximation instead of the linear approximation. You don't get a normal distribution, that's true. I'm using these techniques not for the stability of criteria, such as a Cramer type of statistic or a chi-square type of statistic, but for the solutions, for the parameters. And in the case of these parameter estimates, for instance, the factor loadings or the, what else? The object scores, the category quantifications, statistics like that. It is theoretically possible that they sometimes have a zero derivative, of course. But that would be a case like, I mean, everything can have a zero derivative at some places, just by accident or because, not structurally. So the typical situation here is that there's a non-zero derivative. If you happen to find a zero derivative in the sample, then of course you cannot apply the technique anyway, because then the covariance matrix blows up. The inverse of the covariance matrix blows up and cannot give you confidence ellipsoid. Well, if you find it in the transformation, you also find it in the covariance matrix. Oh, you mean just one direction?
Oh, just in the neighborhood of a point.
Yeah. Well, the matrix of partial derivatives is a linear part of the expression for the covariance matrix of the transform statistic. So if your partial derivative matrix is going to be singular, your covariance matrix is going to be singular, which means that your confidence region is undefined. Yeah. Yeah. Here are some examples for confidence ellipsoids computed for the program ANACOR, which I probably haven't mentioned yet, but it's the program for correspondence analysis that we use. It's not an alternating least squares program because it uses the singular value decomposition. Usually correspondence analysis problems are not that big, so you can use the complete singular value decomposition. As a matter of fact, if you want to compute confidence ellipsoids, you must use the singular value decomposition because you need the derivatives of the eigenvectors, the singular vectors, and the derivatives of the singular vectors involve all eigenvalues and all other eigenvectors. So you must have more information than just the information you need for the representation. Now these ellipses here are 95% confidence regions, marginal confidence regions for each of the points in the picture. This is the Japanese religion example. Remember, there were 6 questions which were asked of about 4,000 Japanese persons, whether they visited graves and read Buddhist scriptures, yes or no. Each of the questions have 2 categories. 2 categories of a question in correspondence analysis are always on both sides of the origin. If the yes is here, then the no is there. If the no is there, then the yes is here. So you have a double representation for the yeses and nos. And the 95% ellipsoids show you that the representation is fairly stable, which is of course not surprising with 4,000 persons in the sample, and there's no overlap, at least almost no overlap, between the sampling distributions of these category quantifications. The stars in the middle of the ellipsoids are the bootstrap points, which I shall come to later. I'll leave this example here for the bootstrap exposition. Again, future activities. Future activities that must be undertaken is to derive the necessary derivatives for an application of the delta method to all techniques. These derivatives can be, and usually are, pretty complicated. They're of course simplest for all eigenvalue-based techniques, such as multiple correspondence analysis, homogeneity analysis, and ordinary correspondence analysis. So we have already worked them out and used them for HOMALS, ANACOR, which is correspondence analysis, PRIMALS, which is one-dimensional homogeneity analysis, and ANAPROF, which is a form of multiple correspondence analysis for profiles. Israel's, I just showed you his 1984 Psychometrica paper with the happiness and the well-being research, is working on the partial derivatives and consequently on the confidence ellipsoids for nonlinear multiple regression and nonlinear redundancy analysis and nonlinear canonical analysis. These are all very long and nasty formulas. The main thing is to work them out and to program them without error, of course. So it's not really very interesting that you would want to bore your audience with. The second type of future results which comes out of this particular project is to apply the two-step model to Lisrel and related techniques. That is, as I pointed out earlier, you can now have consistent estimates for models in which you do not assume that there are linear regressions, let alone that the data are a sample from a multivariate normal, but you can actually use the techniques in situations where the only assumption you have to make is that all regressions can be linearized, can be scored in such a way that the regressions become linear. And you can do that by using the standard Lisrel standard errors for correlation coefficients. And one other part of this project is to construct a test for the linearity of regressions, for the linearizability of regressions, I should say. This is also done by somebody who's writing a PhD about it. So also work in progress. After the delta method, we shall briefly mention the bootstrap. Bootstrap is a beautiful, simple idea and consequently can be described very briefly. We know that the asymptotic distribution of the observed proportions given the theoretical proportions or the population proportions is a multivariate normal with dispersion V of pi, which is pi minus pi prime. Now suppose we draw a random sample with replacement from our observations. This is something which was mentioned in the introduction, is create your own stochastic environment. Don't believe models. which impose randomness on the data simply take care of the randomness yourself by drawing a random sample from your sample. This gives something which we call P tilde of n. And you draw it from the multinomial from your data, which means in this case the observed vector of proportions P bar. Draw a random sample of the same size as the random sample you originally had from your data. This gives you P tilde. Now it's true that P tilde conditional on the observed proportions, and it's a multivariate normal distribution asymptotically with a dispersion matrix which is P, large P, n minus Pn prime, where Pn is the vector of observed proportions. And because Vpn converges in probability to V pi, we can use this conditional distribution by sampling from the data as an approximation of the sampling distribution. And not only that, you can also, any statistic which can be computed from the sampling distribution can also be computed from the bootstrap distribution, and the bootstrap distribution of the statistics is an approximation to the sampling distribution of the statistic. Not only is it an approximation to the sampling distribution, but it's a good approximation in the sense that it asymptotically has the same variance-covariance matrix, and that it asymptotically converges to the same value. This amounts to drawing random samples from your own data, or from anybody else's data, but from the data, and to make inferences to the population on the basis of the samples you draw from your own data. In many recent publications, there's a list of publications here, they're almost all in the Annals of Statistics, and you can find them there. Efron, Beran, Friedman, Diaconis, many populations with bootstrap in the title, and these can be looked up in the Annals of Statistics. In many of these recent publications has been shown that bootstrap methods are both robust in a technical sense and efficient also in a technical sense, which I shall not explain now. It's the regular statistical sense of the words in many circumstances. Now, as an example of the bootstrap, I mean, perhaps it is sort of convenient to explain what the physical operation of bootstrapping is, how you would go about it. For instance, this Japanese example, I have 4,000 Japanese which are listed, and we know the answers of these Japanese to 6 questions. So there's a list of 4,000 times 6, 4,000 rows of a matrix with 6 columns. Now take a random sample of size 4,000 with replacement from this matrix. This does not mean, of course, that you get exactly the same matrix, because it's with replacement. It's possible that some elements which were in your original matrix are not in your bootstrap sample, and some elements which were in your original matrix, maybe 3 or 4 or 5, or maybe ultimately only 4,000 terms with vanishing probability, maybe 4,000 times in your bootstrap sample. So the fact that it's with replacement, of course, extremely important. Otherwise, it would be entirely trivial. You draw a sample, and on this bootstrap sample, you apply your technique again and record the results. That's theoretically all you have to do, and you have to compute theoretically again what will be the result of this operation. If you cannot do it theoretically, then you use the Monte Carlo version of the bootstrap, which is simply draw a bootstrap sample, then draw another bootstrap sample, then draw another bootstrap sample, and collect the results after you've done enough bootstrapping, or after you ran out of computer time. Yes?
On that robust, you're not meaning to suggest that it's not sensitive to outliers?
No.
Right.
No, it's locally asymptotically efficient. But it means that it is continuous in the observations and behaves locally quite well. But of course, it's as sensitive to outliers. Its sensitivity to outliers is dependent on the type of technique that you apply it to. So the mean bootstrapped will be as sensitive as the ordinary mean, and the median will be less sensitive because the ordinary median is less sensitive. Here are 10 bootstrap samples of the Japanese, which are probably inside out, upside down. Yes. And they're drawn in the confidence ellipsoids given by the delta method to show that they roughly give the same information as the delta method. Roughly, because each of these vectors is within the 95, it's a 95% ellipse. Which is, of course, a nice result. You would hope that two asymptotically equivalent techniques for studying statistical stability would also give you approximately the same information. So this is one example where the bootstrap technique works rather nicely. 174. Oh well. Okay, here's another one. This is the political science example that I talked about before the break. It's the category transformations of the various variables. There are these 7 attitude type variables, attitude towards 7 issues, and here are the 4 preference items. Preference for party 1, preference for party 2, preference for party 4. In this plot you have the original category transformations, solid lines, and you have the means of 10 bootstrap samples, dotted lines. The first thing you see is that the two things do not deviate a great deal. And the second thing that you see, of course, is that the mean of the 10 bootstrap samples usually give you a smoother transformation than the category quantifications of one single analysis. This, of course, is entirely logical. You get bumps in your transformation because of idiosyncrasies of your data structure, because of outliers and what have you. And if you're bootstrapping those data structures, then of course some outliers will not be represented in some bootstrap samples. Other outliers will be overrepresented, but on the average you will get a smoother picture. Another thing, of course, is what you see is that the original transformation by definition is a step function, because it's a discrete ordinal transformation in this case. If you're using the bootstrap, of course, and averaging the bootstrap samples, then it's not a step function anymore, and you get smoother. Well, it's still a step function in the sense that it's the same within each interval, but the original transformation, because it's a monotonic transformation, creates larger steps. You know the behavior of this monotone regression algorithm. It creates steps if the correct order is violated, then it makes larger steps, make blocks. Now these blocks do not occur in the bootstrap samples, or not necessarily on the same place, and consequently the average bootstrap looks smoother than the monotone regression for one single analysis. Yes?
Did you do any test of statistical significance of the difference for the usual ordinal scoring, 1, 2, 3, 4, 5, 6, 7, 8, 9 versus...
In this case?
Yes. Be interesting to see it.
You could do that. I mean, given the information that we have computed, it would be very easy to do a test of statistical significance for this scoring system, whether it's really better than the 1, 2, 3, 4, 5, 6 scoring system. But we have not done it. If somebody is interested in that particular test, and it would perhaps be interesting in this example to study this, because it's a reasonably well-behaved example in which you sort of expect that will not make too much difference, then you could perform this test given the information that we compute with either the bootstrap or the delta method.
It would seem like one way to strengthen your case that the scoring makes a difference people seem to respond somewhat to the statistical, significance test.
Yeah, well, this is something which is a difficult point. I mean, you should not reinforce bad habits, of course. That's another way of looking at it. And you must try to sell your product, and you should not reinforce bad habits. Unfortunately, these two things go in extremely opposite directions.
This is an example where you wouldn't expect to find much difference.
This is an example in which you actually do not find much difference.
You wouldn't expect that any scoring would, any reasonable scoring would be good.
Would be pretty good, yes. I agree.
That would depend on sample size. I'm not sure I would agree right off the bat with that. I think that, right, we're talking about standard errors. I guess there's two different questions. Maybe in terms of practical significance, it probably doesn't matter, but in statistical significance, depending on sample size and
Oh, yeah.
it may make a difference.
Yes. It is, well, this is not a large sample. This is just the 150 members of parliament. So here, situation is, it's not a large sample. So I don't think there are any real pronounced differences. But if you, for the 4,000 Japanese, the situation is entirely different, of course. Here's another example, also based on the same data, the 150 members of parliament. This is again a transformation of the 7 issues. In the journal there's another page which gives the transformation for the 4 political parties, but I have no transparency of that. And again, it's one way of showing what the bootstrap does. It now gives the range of the 10 bootstrap samples as a vertical bar, and it gives the bootstrap means as crosses, and it gives the original values as O's, all in the same picture. So the bootstrap means, we have already seen the bootstrap means in the previous transparency, of course. We've also all seen the original values in the previous transparency. This one also gives you the ranges for the bootstrap transformations. There are 10 bootstraps, which is not much, but it's very easy to see what it does to your computing time, by the way. It multiplies it by a factor of 10. And if you do 100 bootstraps, which is of course better, that's one of the big examples of creating your own, where creating your own stochastic environment is handy, because you can go on drawing bootstrap samples as long as you want to, or as long as you care to. But each time you have to repeat this canonical analysis method, and that can make it quite expensive, of course. If you do it 100 times, your computing time goes up by a factor of 100.
Isn't more than one stationary point that going to create problems?
That could very well create problems, but not problems which you cannot detect if you plot your individual bootstrap values. That means, of course, that another way of putting this is that if you're doing a bootstrap study, then at the same time you get information about sensitivity to the local minimum problem. If you plot your solutions all in the same plot, as is done here for the transformations, but that's perhaps not a good example. You can also do it for the two-dimensional projections, for the loadings, for instance. If the loadings are in 10 bootstrap samples, nine of them are exactly the same, but the 10th is very different, then you have probably discovered the local minimum. And if you do it routinely and only compute the average of the bootstrap values, then you would sort of do something which is risky. But if you really look at the different values for your bootstrap transformation, then you can use it to your advantage in that respect.
If you assume that you've got a procedure that's pretty stable. If you're in a situation where really you've got naturally a lot of fluctuation, then you...
Well, whether the procedure is really stable or not is of course, that is important consideration in many situations. But I mean,
in this sense, stable in this sense.
Oh, okay.
That if you really have very wide bounds, then you're not going to be able to tell the difference between having samples.
Of course, then you cannot distinguish, let's say, sampling variability from local minima problems. True.
I have a question on that.
Yeah.
I appreciate the practical constraints in generating enough samples in this bootstrap situation, but do you have evidence that 10 would be enough? Because I haven't seen.
I will come to that in about 2 seconds. Future research in progress. How many samples are needed? That's one question. And the other question is how to best implement the bootstrap. Second aspect, of course, is concerned with these practical constraints. The first aspect is a little bit more of theoretical relevance. There's a study in progress also by somebody who's doing his PhD on this particular topic, who uses analysis of variance techniques to find out when to stop bootstrapping. Probably that's one way of phrasing the question. Adding a bootstrap sample gives you extra information, of course, so in that sense it's better to continue until you're blue in the face. But I don't know if that's a Dutch expression or an American one. But anyway, at some point, things that you're estimating, the variability, the ellipses, are not changing a great deal anymore. And you can sort of extrapolate what would happen if you would continue with your bootstrap procedure. And in the cases which we have been investigating, and it's mainly using the Vlaardingen-Vlachtwedde example that I showed you, the lung study, which is pretty large. It's, let me see, something like 2,000 people, I think, or pretty big. There, things did not change at all after more than 25 bootstraps. And things are the category quantifications and the loadings and things like that. And after 10 bootstraps, things were pretty stable. Like what you, for practical purposes, stable enough. No qualitative changes anymore. But it could very well be true that if the sample is small, then more bootstraps are needed to get stable information about the variability. I mean, you would expect something like that, of course. But of course, if the sample is small, bootstrapping is cheaper. So there's a fortunate trade-off there. Most trade-offs are unfortunate. That's somebody's law, Murphy, I think. But this one is good. This is the bootstrap. The other thing we mentioned is the jackknife. Jackknife is probably more familiar, certainly older. And the jackknife consists of deleting one observation and then doing your analysis again, first observation, then doing your analysis again, deleting the second observation, then doing your analysis again, and doing this for all observations in turn. And if you're done, you combine the results in a smart way, and that gives you A, a method for bias correction, which you can also get from the bootstrap, by the way, and B, it gives you a method to estimate your sampling distribution and your standard errors. This, I mean, jackknife is more or less a standard statistical tool, so I will not elaborate on it. But there are some equations in the transparencies. There's much more information in the book by Gifi on this particular application of the jackknife. Future project is comparison of bootstrap and jackknife. We've already done that. There are some, asymptotically the two methods are the same, of course, and that is also standard in the statistical literature. But it's very easy to see that the bootstrap introduces a much larger perturbation of your data than the jackknife. If you have 4,000 Japanese and you throw out the first one and you repeat your analysis, then it would be extremely strange if you found completely different results. What? Okay. But the perturbation introduced by the bootstrap is far more radical. The difference between the bootstrap sample and the original sample will be much larger than the difference between the jackknife sample and the original sample. So you would expect some differences there, and we have found some pretty dramatic differences which have to do with the perhaps with the precision in which you perform your computations. I think that the jackknife method is far more susceptible to the low precision because, well, basically, it's a technical question. I don't know if I should mention it because we're sort of running late. But the differences between the jackknife value and the original value are combined to pseudo values in the jackknife. And in order to do that, you multiply the original value by n, and you multiply the jackknife value by n minus 1, and then you combine the two by subtracting them. Now, if there's a large difference in precision of your techniques, it's going to be multiplied a great deal by this factor n that is in here. And that is basically what happens in the applications we have seen so far. And this factor n is exactly due to the fact that the perturbation you introduce is so small. It is meant to compensate for the fact that you're introducing a very small perturbation. You multiply by n again to compensate for that. But this will sort of put a very heavy burden on the precision of your computing methods, and our computing methods do not have that precision. So in that sense, the bootstrap, which introduces a far larger perturbation, gives results which are very similar to the delta method, which you can use as a gauge in this case. And the jackknife method gives results which are sometimes completely and surprisingly different.
When you say precision,
Yes.
you don't mean numerical.
I mean numerical precision. The number of decimals you use to compute your solutions in. If you do a jackknife study on the performance of overalls, for instance, and you do it in Fortran with single precision, 4 decimals precision in the loss function, and you compare that with an APL version of the same program which uses 16 decimals precision, then you get completely different results from your jackknife study. And you get exactly the same results from your bootstrap study. This was a case in which n was equal to 1200 or something like that.
Well, yeah, I mean, I think it's simply a question. It is simply a question of the end.
Yeah, you're multiplying the error, really.
Multiply by 1,000 and you're losing pretty significant figures.
Yes. True. But it means that either you must make your programs much more expensive by demanding much higher precision, or you must not use the jackknife with a bootstrap.
Well, it seems to me, I mean, if you get a double precision product, then you get it at no cost.
That could be true. Well, that does make it more expensive, of course.
No, I mean, if in your computer you get a double precision result in the multiplication.
Okay. But I mean, an additional, I mean, it's, yeah, true.
When one is jackknifing with a large sample, one usually deletes more than one observation at a time anyway. So I would think that would tend to help compensate for the precision problem.
Yes. There are many variations on jackknifing which I have not mentioned. One of them is deleting more observations at the same time. Another one is random jackknifing, in which you do not delete all systematic subsets of k observations, but in which you delete random subsets of k observations. There's subsampling, all these things you can use, but the important thing is I think the bootstrap and the jackknife are sort of extremes in this respect, and this is one result we have. Significance testing. We also do that. And in this case, it's significance testing of generalized canonical correlations. What are generalized canonical correlations? If you formulate the M-set canonical correlation problem in terms of the C matrix and the D matrix, the Bird table and its diagonal, where the diagonal is augmented in this case because you have the within set information on the diagonal, then the eigenvalues of that particular problem, which are in the case of multiple correspondence analysis, the eigenvalues of the birth table, and in the case of principal component analysis, the eigenvalues of the correlation matrix. The eigenvalues of the problem are called generalized canonical correlations. Of course, in the case of canonical correlation analysis, they are the canonical correlations. In order to do significance testing here, and we're basically testing this, the null hypothesis of independence, complete independence, we use permutation methods. Let us consider the situation in which the variables are partitioned into sets. And you have n observations on all of these variables, but the variables are partitioned into sets, either sets of dependent and independent variables or a more complicated structure with more than 2 sets. You leave set 1 as it is. You take the second set and you permute all distributions randomly, all observations randomly, so a completely disarray of your subjects or individuals or objects or whatever they may be. Then you take the third set and you also permute that randomly and independently of the second set. And you go on until you have permuted all sets. Now this process defines your null distribution. So your null distribution is a random permutation distribution of all sets. I'm leaving the first set intact, of course, because you might as well. I mean, you could also permute them all, but that's not necessary. There are various ways in which this null distribution can be computed. The first way is by enumeration. Enumeration is a technique you use if you're testing independence in a 2 times 2 table in Fisher's exact test. It is not advisable to try enumeration in really multivariate cases, because then, of course, the number of possibilities is far too large, and you get these interesting calculations that it would take you that many ages or length of the total existence of the universe or distance to the nearest star, I don't know, calculations like that. So enumeration can only be used for very small examples. The other thing is to use asymptotic approximations, asymptotic normality of the permutation distribution. The asymptotic normality of the permutation distribution is very easy to demonstrate and gives you asymptotic normality of the birth table under the permutation distribution. This is used in a delta method context, not in the permutation context, but the results are really the same. In papers by Lebar, in Comstead, 76, I think, and by O'Neill in the Journal of the Royal Statistical Society, to test the significance of the eigenvalues of correspondence analysis. So you can use that in a very simple situation to test the eigenvalues of ordinary correspondence analysis. And the third way of evaluating the permutation distribution is by Monte Carlo methods. And that simply means, in one case, generating these permutations directly and doing that a number of times, repeating that a number of times. Computer-intensive statistics again. And the second Monte Carlo method uses the asymptotic normality of the birth table and takes random samples from that asymptotically normal distribution. That's much quicker, but a little bit less direct. But it's also a Monte Carlo method. There's a paper on this procedure for testing the significance of these generalized canonical correlations by me and Van der Burg. It's not out yet, but it will appear in volume 4 of this data analysis and informatics series. That's the series where these papers are also from. Proceedings of a symposium in Versailles. Volume 4, I think the conference is right now, at this moment, or something like that. And the paper is perhaps presented at this very time, although it's 10:30 in the evening, so probably not. But it will be out in another half year, and it lists many of these examples, some of which I will show you. This is applying the permutation techniques to the from year to year data. This is one of these school career examples that I mentioned. And We have analyzed them with various options, multiple nominal, single nominal, and numerical in 2 dimensions. The first line of the table that says EV gives the observed value of the canonical correlation. The next lines give the percentiles of the sampling distribution, the permutation distribution of the statistic. And what you see here is that this one is larger than the 95 percentile, and consequently it's significant, to use that word, on the 5% level. You also find that the second dimension canonical correlation coefficient is significant on the 5% level. This is, by the way, computed by the random permutation method, which is the version of the Monte Carlo method which directly generates random permutations. The second table here is computed by the C-matrix method. That is the indirect Monte Carlo method, which generates asymptotically normal, or which uses asymptotic normality. And you can compare the 2 sampling distributions, or the 2 estimates of the permutation distribution, and they are very similar. So that is sort of a nice result, that they are very similar, because it shows you that the 2 approximations are really approximating the same thing. Yeah.
How do these permutation methods compare to bootstrap?
They're both computer intensive.
No, I meant in terms of standard errors and that sort of thing.
Well, in a bootstrap, you're not testing a null situation. You're not sort of assuming that there is no relationship whatsoever in the data, and the permutation methods are sort of based on that particular assumption. So if you can also apply the bootstrap in this case, but it will give you other information. It will not give you test of the. Well, the problem is, perhaps it's best to explain it. If you look, for instance, at the eigenvalues of correspondence analysis, or of multiple correspondence, any of these eigenvalue things. In the bootstrap or in the delta method, you use asymptotic normality, which comes from the local linearity of these eigenvalues, the fact that they are differentiable. But in these null situations, all eigenvalues are equal in the population. There is no, or they're all 0 even. So all eigenvalues are equal and they are not differentiable. If the eigenvalues in the populations are equal, they're not differentiable functions. So the whole machinery of the delta method and the bootstrap cannot be used in null situations. But this you can use in null situations. As a matter of fact, you define this null situation. Of course, it's this permutation distribution implies that there is no relationship at all in your data in the population of permutations. So this is a null situation in which you can do something by using this permutation distribution, but the regular bootstrap and delta method theory does not apply. I think we are almost, well, we are already over hours. It's briefly, this is an application of the C-matrix method and the random permutation method of the Russat data. I've shown you the Russat data yesterday. There were these countries which were classified on a number of economic variables and on a number of political variables, which had to do with the relationship between political stability and economic prosperity. There was a canonical analysis example taken from the book by Gifi. Now here the situation is quite different. This is only a small sample. There are only 50 countries or something like that. And here you see that the first dimension of canonical analysis is not significant on the 5% level. And the second dimension is not significant on the, well, somewhere between these two. And in the numerical case, the first dimension is significant on the 5% level, but the second dimension, again, is not significant. Here, in the C-matrix method, you estimate the same things, and you only have to compare this, and it shows that there are discrepancies between the permutation method and the C-matrix, which are logical because you're only dealing with a small sample here. So this tells you that such a significant procedure, certainly in the case of small samples, is very useful because you could very well be interpreting results which are not really there in this sense, which you could also find if you applied your technique to data which have no structure at all. This is the same example, the russet example. This is the permutation distribution of the eigenvalues. In this case, of the canonical correlation coefficients. And below the picture it says what the eigenvalue was 0.815. The significance probability is 0.11. So it's not significant on the 5% level. The second dimension had eigenvalue this and significance probability 0.41. In the numerical case, you find a significance probability of 0.01, and for the second dimension, 0.31. So this is one way of studying significance of the solutions you compute by using these nonlinear multivariate analysis techniques. Unfortunately, I will not be able to finish the last 10 transparencies, which were about causal analysis. But you can get copies of the transparencies. So unless I continue, which is perfectly all right with me, but perhaps not with you.
If some people would like to leave, that would be fine, but I would like to stay.
Okay. It will take me about another half hour, I would say.
Do you think it's particularly important to look at such permutation distributions before taking seriously the results?
Yes, almost by definition.
So you're really talking about very computer intensive.
Yes. Well, there is of course a point. There is of course the question how these procedures are best implemented. If you're, for instance, if you're bootstrapping, you could of course use the information. You could use your original solution as a starting point for your bootstrap samples, and that would save you a lot of computer time, of course, because it would be a very nice starting point. On the other hand, it would bias.
You got a pretty good size sample.
Yeah. On the other hand, it would bias you towards making more stable assessments than would generally be the case, because you're sort of building in stability by using the original sample as a starting point.
In terms of missing the other stationary points?
Certainly missing the other stationary points, if there are any. All right. We continue. First, some possibilities for partial canonical correlation analysis. Partial canonical correlation analysis partitions out certain sets of variables before it starts to work. Now, can you also partition out sets of variables and still use this idea of optimal quantification? That is a question. The answer is yes. How can you incorporate partial canonical correlation in overalls? You can do that by using copies of a variable in different sets of variables. So if you have a particular variable that you want to partition out, for instance age, and you're doing a two-set canonical analysis, then you put age in the first set and you put age in the second set. Now what happens? What happens, of course, is that it finds one canonical correlation equal to 1, which is defined by age. But because all other canonical correlations are orthogonal to the, let's say, to the first canonical correlation, all other quantifications and quantification systems and object scores that you find for the other dimensions of canonical analysis will be orthogonal to age, and will consequently age will be partialed out. And if you use p copies of age, you can even use age. Well, this is numerical age, but if you have a nominal age, you have categorized age into categories and then use that as a variable. If you have a nominal age and you use p copies of age in the first set and p copies of age in the second set, then you're even partialing out age multiply. As it were, you're partialing out linear age, quadratic age, cubic age, all functions of age. So in a statistical sense, you're really studying independence of age and not only orthogonality. You're working independent of age and not only orthogonal to age. So this is one way of incorporating the idea of partial correlation, in this case of partial canonical correlation, into overalls. You must take care, of course, that the variable that you're doing this to, age in this case, gets the same quantification in all sets in which you introduce it. That's for a numerical variable, that's easy because it's already quantified, but for a nominal variable, it means a restriction on the quantifications. If you allow for different quantifications of the variable in both sets, then this whole idea does not apply anymore, and it's wrong. So you have to impose this restriction if you want to use this idea. But otherwise, of course, it's a fairly simple incorporation into the nonlinear multivariate analysis programs. And of course, using this partial idea already is one step in the direction of what is known as causal analysis. You need to introduce this set structure. You need to say that some variables must be partialed out, and you can also build up in this way a path diagram by partialing out variables, studying relationships, and then going back in the path diagram. We've already seen one example of that in the Israel's paper, which did not really partial out anything, but which used different combinations of analysis to build up a path diagram. Possibilities for causal analysis. First I'll tell you something about the status of that project. I'm not particularly fond of the term causal analysis. I'm always using these apostrophes to around the term. If you want to know why I'm not particularly fond of it, you must read the September issue of Psychometrica, in which there is a review of 4 or 5 books on causal analysis. And I give several reasons there why the use of the terminology by social scientists is sort of unfortunate. Of course, the fact that the terminology is unfortunate does not imply in any sense of the word that the techniques are faulty. It merely implies that you have to be careful with your presentation of the results, and that of course is true for all techniques. The problem with causal analysis, or with path analysis, I think I would prefer the word path analysis. The problem with path analysis is, for practical purposes from our point of view, it does not fit directly into the Gifi system. The Gifi system was built around multiple correspondence analysis, or principal component analysis if you would like. It was possible to fit in some of the common, let's say, exploratory multivariate analysis techniques: principal component analysis, canonical correlation analysis, regression analysis, multivariate analysis of variance. Techniques which are relatively unstructured in terms of dependent and independent variables. 2 sets or more sets which enter in exactly the same way. But the essence of causal analysis, of course, is that each variable has a different set of independent and dependent variables associated with it, and that the notion of dependent and independent variables is far more subtle and far specified in much more detail than in ordinary regression or component analysis. So you need a somewhat more general loss function. There is the loss function. Actually, there's one on top and there's one somewhere in the middle of the transparency. The G's again are the indicator matrix, the Y's again are the category quantifications. I'm summing now over all endogenous variables in the path diagram. I shall later explain what I mean by path diagram, but I think the notion of an endogenous variable is probably well known. A variable is endogenous if it is influenced by other variables in the system. It's exogenous if it's on the border of the system and not influenced by any other variables. So I'm using each one of the endogenous variables as a pivot in these summations, and the things that influence the endogenous variable, which are different in general for each endogenous variable. And you could call that a set of causes. You could also call that a set of paths, of direct influences on the endogenous variable. For normalization purposes, it's convenient to use a slightly different representation of the loss function. You require this, which means that all variables are normalized, and you insert something which is a bit sloppy, but it's a matrix B, and it's the matrix of regression coefficients, of course, or path coefficients if you prefer that terminology in this context. And this symbol here means that you repeat what's in the brackets before it, of course. It's also brief. So here you have each endogenous variable which must be approximated by a linear combination of its direct causes, and the linear combination also involves quantification of each of the variables. And of course, these quantifications are completely free in the sense that all the options of the Gifi system can be applied to it. They can be multiple, they can be single, they can be ordinal, they can be numerical, they can be everything you please, as a matter of fact. So on the quantification part, this particular part, everything I've said about these nonlinear multivariate analysis techniques remains true. The only thing is that the loss function is a little bit different now, because here in the Gifi loss function you had this latent variable matrix, the x's, the object scores, with which everything was compared. Every other quantification of the variables, every other set of variables was compared with a single set x. In this case, you take each of the endogenous variables in turn as a target, and you use the direct causes of that endogenous variable to determine the transformations and the linear combinations. Let us explain the basic idea behind this loss function. This is not directly related to anything having to do with the Gifi system. It's just a general sort of discussion of causal analysis. A causal model is a D-graph, directed graph, an arrow diagram. That's another way in which you can formulate it. Exogenous variables in this arrow diagram are sources, by which I mean that only arrows depart from them and no arrows arrive at them. Another word you sometimes see is transmitters. Sources is the opposite of sinks, of course, and transmitters is the opposite of receivers. But exogenous variables are transmitters. Arrows only depart from them and do not arrive. The relationship pictures in the graph is, in words, is a direct cause of. I'm now not using the word cause between apostrophes anymore, because I have defined it. And of course, if you define something, there's no trouble. You can define it anything you damn well please. It's only in, let's say, informal methodological discussion that I've used the word cause between apostrophes. And here I'm sort of tempting. Well, of course, it's still risky, but I'm using the definitions anyway. And the change in the graph, so the arrows define is a direct cause of, and the change, for instance, this chain here defines is a cause of. Another thing we assume is that causal graphs are transitive. So there's no path which leads back. There's no way, if you can get from E to G, then there's no way you can get from G to E. Yes? Yes.
Is that part of the system, or is that just something? I mean, that is a difference from standard path analysis, where you can have reciprocal causation, feedback calculations.
Well, it's many things at the same time, really. It's at the moment it is a part of the system, and I'm not sure whether it's something which I really want to change. because I think the notion of reciprocal causation is very problematical. And if you read literature about it, it's usually associated with processes in which causality is really unidirectional, but the measurements are so close together that you cannot distinguish the feedback loop from the other loop. And if you had more information, you could write it out and it would be unidirectional again. That's the usual, let's say, explanation of reciprocal causation. And of course, in the philosophical discussions of causation, you usually find that it cannot bend back on itself in the same sense. So I'm not really sure whether I want to put it in at some point. It's for the moment it is let's say convenient to limit ourselves to transitive graphs, but perhaps at some point. There are methods of dealing with it even in this graph context. Of course, you can talk of block causality and
Instrumental variables.
yes, and things like that. And these tricks are really used to be able to deal with these reciprocal causation situations. And we could also incorporate these, but I'm now dealing with let's say the simplest case. There are many things you can define within this graph in terms of the arrow structure. Here are the let's say the edges or the knots or the objects that you're defining, the variables that you're defining the structure between, A all the way up to H. In this table I first give the direct causes. A, B and C have no direct causes. They are exogenous variables. These are the direct causes of the other variables. They all have two direct causes. These are the causes, the direct and the indirect causes. These are the levels. Now what's the level of a variable? The level of a variable is 0 if the variable is exogenous. If the variable is not exogenous, then the level is equal to 1 plus the largest level of its direct causes. So if you have the list of direct causes, you look at the largest level of these direct causes, which then already determined, and you get this level assignment here. Exogenous variables get level 0. D and E have all direct causes of level 0 and consequently get level 1. F has D as a direct cause, consequently gets level 2. And G has A as a direct cause and also gets level 2. And H has H has G as a direct cause and consequently gets level 3. And then there's another relationship also defined now in terms of this level assignment. You call something a predecessor if it has a lower level. And here's the list of predecessors of each of these things. This is let's say, an extension of this relationship, and this relationship is an extension of that relationship. Because, well, that's fairly easy to see. What is the idea behind path analysis? Let's say the qualitative idea. It says semi-quantitative there, but that's supposed to be the same thing as qualitative. It is already a little bit of a translation from the pure qualitative graph to something which is in terms of independence. The first idea is that a variable is independent of its predecessors given its direct causes. It's perhaps better to keep the example in the immediate neighborhood.
What is the meaning of predecessor, the graph?
Something with a lower level.
I can't see that in the... So...
I don't know if...
D has a lower level C.
Well, actually it gives the list of predecessors in the last column. The predecessors of H are all others. Yes? The predecessors of G...
What about, take D for instance.
Yeah.
Why are A and B predecessors of D?
Because A and B have level 0. and D has level 1?
Oh, I see that. Thank you.
Okay. The variable must be independent of its predecessors given its direct causes. Now this leads to various conditional independent relationships which I have written down explicitly. Again, you take each endogenous variable in turn, E, F, D, G, H. And this is a notation for conditional independence, which is due, I think, to David, an English statistician. And for instance, this says that E must be independent of B given A and C. Let's look at E. Its direct causes are A and C. Its predecessors are A and B and C. There's always a larger set. So the only thing that's a predecessor and not a direct cause is B. Now that means that E must be independent of B given A and C. So you can read these directly. You can read these directly from the table on the previous page. And in some cases of path analysis, you do not only impose these constraints, but you also impose these constraints. Variables of the same level are independent given their predecessors. So this says something about variables of the same level. So D and E must be independent given A, B, and C. Here are D and E, they're of the same level, both level 1, D and E, and they must be independent given A, B, and C.
So, for this model that you're presenting, it sounds like you're presenting something that's sort of a classical recursive case where
Well,
if
you're using
writing the coefficients for the endogenous variables, it can be written as lower triangular, and in addition, the disturbances
orthogonal.
would be a diagonal matrix, so they're uncorrelated.
Yes, true. If you use these, let's say in the classical sense, then you can use them to factor the probability distribution or the probability density of your variables in the way in which you do that for a recursive model. And you basically use a level assignment to decide which factors you want to successively factor out in your recursive factorization.
Are correlated errors something that could be handled in this?
Well, if you do not make this assumption, then you have correlated errors. This is, again, I do not know whether I want correlated errors or not, because again, the correlated errors is, let's say, methodologically or philosophically, it's a similar problem as reciprocal causation, of course. There are people who say errors cannot be correlated because if they were correlated, it wouldn't be errors. There must be some structure there which causes the correlation, and if there's some structure there which causes the correlation, then the use of the word error is not appropriate. That is an argument you sometimes find. I'm not saying I agree with it. It is an argument you sometimes find. Again, this system is still not entirely quantitative. It's still mainly qualitative because I have not defined what I mean by independence, and I have not defined what I mean by what I think that the edges, the points in the graph are. Now we have to specify these things. I also have not defined how these variables in the conditional independence relation should be combined, whether it's really the case that this is how A, C, and E, I mean, the notation is clear, but it's still not very specific and still not well defined. Now you can define it in various ways, that's why I left it open. The first is that you identify a variable with a subspace of the space of random variables that you're working in. Not necessarily with a vector, which is a second possibility. And the third possibility is that you identify a variable with a cone from which a quantification can be chosen. Corresponding with these choices of the variable are various meanings of the word independence. If you identify variables with subspaces, then independence is best identified with orthogonality of subspaces. For instance, you could define a variable with the set of all, let's say you have the variable age, then you can define the corner or the point in the graph with all transformations, all measurable transformations of the variable age. In that case, you identify the corner in the graph with a subspace of the space that you're working in, the space of all transformations of a given variable. Orthogonality of subspaces in that case is the same thing as independence of the random variables. So this is a very strong but classical interpretation of the graph. So you see that sort of in steps we're introducing more and more distinct and well-defined ideas into the picture. We start at purely quantitative level, then introduce the general idea of conditional independence, which is sort of not really defined but obvious what sort of thing it would be. And now we are really defining the notion of conditional independence, and we find it can be done in various ways. There's also the possibility of identifying a variable with a vector. That's also classical, of course. I mean, you don't, if you have age, you simply identify it, the corner of the graph, the thing that you're studying, with that particular vector of measurements. In that case, independence should be defined in terms of orthogonality of vectors, not of orthogonality of subspaces, because you do not have subspaces, and orthogonality of vectors in this case means uncorrelatedness. So instead of independence, you then have uncorrelatedness. If your variable is basically unknown, but you can choose it from a cone, then again, you're still working with vectors, except for the fact that it's temporarily unknown, and you should use orthogonality of vectors as your notion of independence. With red, I've indicated the cases that would correspond with these three different choices. Choosing variables as vectors and using orthogonality of vectors as the independent notion, uncorrelatedness, which conditionally means partial correlations that vanish, is the classical path analysis case. And of course, it's not only path analysis, also multiple regression, partial correlation analysis. All these things are all special cases of this general setup. Just depends on how you specify the path diagram. So this is also called the Simon-Blalock approach or the Sewell-Wright approach, depending on what particular field of science you happen to be working in. The more strict interpretation up here could be identified with log linear analysis, if you wanted to. Let's say the path analysis or the conditional independence form of log linear analysis, which works with independence instead of uncorrelatedness. And there is one important special case in which these two notions are equivalent, and that's of course the multivariate normal distribution, in which uncorrelatedness is the same thing as independence. I think in the very first lecture on Monday I mentioned that as a very important property of the multivariate normal distribution, and here again it appears as a very important property in which these two approaches to path analysis are equivalent. The third one is new. If you do not know your variable but you can select it from a cone, then of course you have something similar to the optimal quantification type of techniques that we have been talking about before. Now there's in the literature there has been a distinction which has been popularized mainly by Herman Wold for reasons that I will probably mention a little bit later on. He has contrasted the prediction-oriented approach to fitting of causal models with the statistical or estimation-oriented approach. The prediction-oriented approach typically works as we do with the least squares loss function and finds out if and in how far a variable is in the space spanned by its direct causes. So there's a difference here. The system we have set up of these various causal analysis models does not assume that the residuals vanish. The system here assumes that the residuals are orthogonal. Now this is an extremely important difference, of course. If you have completely unrelated random variables with zero correlations, between them, then of course you have a very poor prediction, no prediction at all virtually, and you have a perfect fit of all these models, because by definition the residuals are orthogonal or uncorrelated or independent. But this is an important point. I mean, Lisrel fits perfectly well if you apply it to random data, no matter how you specify the model. But it gives a very poor prediction or a very poor explanation of its key variables in that case, of course. So this is the more or less the difference between the prediction-oriented approach and the fitting approach. And we are closer, at least in the current implementations of the technique, to the prediction-oriented approach. We want the residuals to be zero and not merely to be orthogonal or independent. Key result, however, in recursive path models, in which all variables are numerical, the prediction and the model fitting approaches for numerical variables, I already said they were numerical, are equivalent. This is a result which has been proven by Wold in 1946, I think. And the equivalence is in the sense that the least squares estimates are the same as the maximum likelihood estimates. If there is missing information of any form, then this is no longer true. Now, missing information in this context can be many things. In the first place, it can be missing information. For instance, observations on some variables can be missing. But it can be more interestingly, it can also be missing information in the sense that some variables are numerical and non-numerical, excuse me. Ordinal or nominal, for instance. This would also be classified under the general idea of missing information, because eventually you're going to find quantifications of these variables, so then the missing information has been filled in. But if you do not know these quantifications, then you have missing information. And there's another form of missing information which is fairly important in these models, and that's the so-called latent variables. The basic idea behind our approach to latent variables in red is that they are variables with a very primitive measurement level. And that is, it's not new actually, I think it's implicit in the work of Wold, but I'm sort of fond of making these things as explicit as possible. Latent variables in the system of measurement levels that we have used in the alternating least squares methods are continuous single nominal. And by this we really mean no restriction at all. There is no measurement restriction on the latent variable. The only thing you know about a latent variable is that it occurs in a particular place in your path diagram, and it has particular relationships with other variables, but you do not know anything about its measurement level. So in this sense, we can simply incorporate latent as a new measurement level in our hierarchy of measurement levels. We have numerical variables, we have ordinal variables, we have nominal variables, and at the bottom end of the scale we have latent variables. You know something about numerical values, a lot. You know their exact values. You know something about ordinal variables. You know their categories and the order of the categories. You know something about nominal variables. You know their categories. You know that things are equal, yes or no. But you do not know anything about latent variables. The only thing you know about latent variables is their place in the structure. Now, emphasizing this particular aspect of latent variables will be very important in our subsequent developments, which I will not discuss here, but simply mention. This is a project we will start, which has started already, but which will formally start in January this year, and which will deal with a number of things. The most important ones perhaps are comparing the various ways of making qualitative path models, graphs, arrow diagrams. Quantitative, that's comparing these various ways of giving a precise mathematical meaning to these qualitative concepts. And the second component of the project is to construct path-als algorithms and to compare these path-als algorithms with LISREL and PLS. There's a sort of a footnote. LISREL and PLS have already been compared in many instances, but according to my opinion, not very well. The main difference between LISREL and PLS is how the missing information is estimated. In PLS and also in our methods, missing information is estimated by least squares and by optimal scaling. And this leads to, in the statistical sense, to inconsistencies. Herman Wold calls this inconsistency consistency in the large, but that of course is merely an excuse. He says if the number of variables goes to infinity, then this inconsistency disappears, which may very well be true, and which is usually true, but which is not very important, because for a finite number of variables, if you're trying to use PLS to estimate a causal model, then you have inconsistent estimates of your structural parameters in the same way as, well, I was going to mention the Rasch model or functional factor analysis models, but that would take us too far, I would say. So there's a certain sort of inconsistency in the PLS-Gifi approach if you think of them as estimating structural statistical models on the basis of random samples. Of course, there's better prediction in higher explained variance in the PLS and Gifi models than in the likelihood, the maximum likelihood approach. In the LISREL maximum likelihood approach, you also fill in your missing information. That's not emphasized very often, because in the usual LISREL algorithm, you do not get estimates of your latent variables. But if you use the EM algorithm, and I'm not suggesting that you should really use the EM algorithm, but you should use the conceptual basis of the EM algorithm. If you use that, it's very easy to see that LISREL also produces, or maximum likelihood, also produces estimates of the missing information. And it turns out that in this case, the transformations or the quantifications of the variables are by conditional expectation and not by optimization of a least squares loss function. And in the statistical case, this means that you have consistency and not inconsistency. So this is another important thing which must be compared in an appropriate way, and not in a sort of loose or computational way in which it has been done so far. Finally, my very last transparency. A new version of the book by Gifi will be published by the DSWO Press, hopefully early 1987, in 3 volumes. And it's a little bit later than I expected, but I hope you enjoyed the seminar, and this is the end of it.
Thank you.
Thank you very much.
Okay.
Thanks, Alan.
Okay.